When you look into a standard flat bathroom mirror, you get a direct copy of reality. Flat mirrors reflect light at equal angles, producing a predictable, same-sized reflection of whatever is in front of them. But if you bring the inside bowl of a shiny stainless steel spoon close to your eye, the reflection changes. Your image is upright but noticeably magnified. Pull that shiny metal spoon away from your face and watch as the image suddenly flips completely upside down. Turn the spoon around to the bulging backside, and you are right side up again, but shrunk to miniature size. A single piece of curved metal changes the rules of reflection. To understand the physics behind this, we have to look at the geometry of a sphere. Instead of a flat sheet of glass, we begin with a hollow glass sphere. In this diagram, you can see a 3D hollow sphere. If we take a clean slice right off the edge, we isolate a single curved piece of glass. This is the foundation for any spherical mirror. Clear glass doesn't reflect light on its own, so we apply a reflective coating, like silver or aluminum. If we paint the outside of this curve, the inner, caved inside, becomes the mirror. We call this a concave mirror. If the manufacturer applies that coating to the inside of the curve instead, the bulging outer surface becomes the mirror. This is a convex mirror. The physical shape of the glass itself remains the same in both cases. Whether the mirror reflects from a cave or a hill depends entirely on which side of the sphere's slice receives the silver paint. Looking at this model, you can see the curved mirror alongside the faint outline of its parent sphere. Because the mirror was cut from a sphere, it inherits that sphere's center point in space, known as the center of curvature. The line drawn from that center to the glass is its radius. Halfway down that radius line sits the focal point. Mathematically, the distance from the mirror to this point is always half the length of the radius. When parallel light rays hit a concave mirror, the inward curve directs those rays together, making them converge at that focal point. This crossing of light rays explains why an image flips upside down. Once an object moves back past that invisible focal point, the light rays cross over each other, inverting the reflection. A convex mirror handles light differently. As you see here, when parallel rays strike its outward bulge, they scatter, diverging away from each other into the room. Because the light scatters outward, those rays never meet in front of the glass. But if you trace those diverging lines backward through the solid mirror, they appear to originate from a hidden focal point trapped behind the surface. The geometry dictates the reality. Concave mirrors force light to converge, creating images that can flip upside down. Convex mirrors force light to scatter, ensuring the reflection remains upright and reduced in size. Engineers use these rules of convergence and divergence to solve practical problems. By keeping an object very close to a concave mirror, inside its focal point, a dentist gets a magnified, upright view of a tooth. Car headlights reverse this process. This diagram shows a light source placed exactly at a concave mirror's focal point. The scattered light hits the back of the bowl and reflects straight outward as a parallel beam. Convex mirrors provide a different utility. Because they scatter light, they naturally shrink the objects in their reflection. This allows a large amount of visual data to fit into a small area. This creates a wide field of view. It is the physics powering your car's side view mirrors and the large mirrors installed at road intersections to help drivers see around blind turns. Looking at this photograph of the James Webb Space Telescope, you can clearly see its massive, segmented, golden concave mirrors. These curves capture and focus incredibly faint light from the distant universe. Back on Earth, the Gran Telescopio Canarias Observatory relies on these same principles. The ability to collect and converge light makes large-scale optical telescopes possible. Mastering the physics of a simple curve allows engineering to solve visual challenges at every scale, from daily driving to mapping the cosmos. Which brings us back to the mystery of the stainless steel spoon. The inside bowl is a concave mirror. Your reflection magnifies when you are very close, and inverts once you pull your face back past its hidden focal point. The back of the spoon is a convex mirror. Because its outer bulge scatters incoming light, your reflection will always be smaller and upright. The strange distortions seen in curved metal are the mathematical result of light interacting with a sliced, silvered sphere.